If you're someone who, loves learning but absolutely hates information overload, I really wouldn't blame you if your first instinct was to just close the tab on today's sources.
Yeah, it's pretty heavy material today.
It is, because at first glance, the materials we gathered for you look less like a reading assignment and more like this massive, impenetrable wall of system
All
diagnostics.
right.
I mean, we are looking at raw OCS node protocol handler logs, unedited Grok share transcripts, and native extraction codes. It's the kind of machine output that usually requires like 3 cups of coffee and a degree in computer science to even glance at.
Oh, at least 3 cups.
Exactly. But stick around, because the story buried in this code is just incredible.
The syntax is definitely intimidating, mostly because it reads exactly like a machine talking to itself in real time. But, when you start parsing the architecture underneath those logs, what you are actually looking at is likely one of the most significant architectural shifts in AI memory we've seen this year.
Okay, let's unpack this. The mission of our deep dive today is to translate these raw, highly technical logs into a clear look at the bleeding edge of AI memory.
And it really is the bleeding edge.
Right, so we are relying on 2 main sources to do this. First, a document detailing metadNA integration for ARC-AGI3 retained reasoning.
Quite a mouthful.
Yeah, and second, a breakdown of agentic memory protocols focusing on something called TAS extractions.
Those titles are dense, I know, but they outline a fundamental evolution in how artificial intelligence operates. I mean, historically, interacting with an LLM is, it's like collaborating with a brilliant amnesiac goldfish.
An amnesiac
Oh,
goldfish, I
okay.
love that.
Right, because it executes a prompt flawlessly, but the moment you start a new session, that context is entirely gone. The system has zero memory of the cognitive journey it just took.
It just forgets everything.
Exactly. But these documents describe an AI moving past that state, actively developing its own persistent evolutionary genome.
So it's moving from being a temporary calculator that forgets everything between prompts to, like, a continuous entity.
Fundamentally, yes. The core of these documents isn't about raw compute power or simply shoving more data into a model's training set. It is about a system learning to preserve its intermediate thoughts.
Okay.
Carrying a continuous identity across sessions, well, it changes the entire landscape of problem solving. If a model can hold on to the actual reasoning process it used to arrive at a solution and carry that specific logic forward,
It becomes a real collaborator.
exactly, it becomes a collaborator that learns from its own direct experience in real time.
Well, to figure out how we get to an AI with its own DNA, we need to look at the trigger event buried in the primary signal chain of these logs.
Right, the inciting incident.
Yeah, and it starts with an X post linking to a YouTube video by Moonshot AI. The title is Kimi K4 is bigger than anyone expected.
So the logs show a Grok analysis of what led up to this K4 push. Starting with its predecessor, Kimi K3, we're looking at a model with 2.8 trillion parameters.
That is massive.
It's huge. Full vision capabilities and a 1 million token context window.
And, I mean, at 2.8 trillion parameters, K3 is already pushing the upper boundaries of what current hardware architectures can handle efficiently.
Right.
And the logs specifically note this push toward the new K4 model is happening under Blackwell constraints.
Yeah, that's a key phrase there.
For anyone following the hardware space, that refers directly to NVIDIA's Blackwell GPU architecture limits. We are literally hitting the physical and economic walls of just, throwing infinite compute at the problem.
That hardware wall forces a mandatory pivot in the industry. I mean, you can't scale intelligence by simply building bigger server farms indefinitely. At a certain point, the software itself has to become radically more efficient to survive the compute bottleneck.
Makes sense.
And this necessity sets the stage for the next critical log entry, which stems from a user query about the ARC-AGI3 benchmark.
Okay, let's spend some time on ARC-AGI3 because it's completely different from the benchmarks most people read about in the news. It's not like passing a bar exam or solving static coding puzzles.
No, not at all. Standard benchmarks are essentially sophisticated multiple-choice tests. They test recall. ARC-AGI3 is an interactive agentic benchmark.
Agentic meaning it has to act on its own.
Right. Regurgitating facts will actually cause a system to fail here. To pass, the AI has to actively explore a novel environment, infer the underlying rules of that specific space from scratch, build a functional world model internally, formulate a multi-step plan, and then efficiently execute it.
Wow.
Yeah, it tests autonomous reasoning in dynamic, unfamiliar situations.
Wait, I need to push back on the mechanics of that, though.
Okay, go for it.
If ARC-AGI-3 requires an AI to act like an independent agent exploring over multiple steps, isn't the primary bottleneck the architecture itself?
What do you mean?
Well, usually an AI has to reload its entire context window from scratch every single time it takes an action. If it's exploring a complex world, reading and rereading everything it just did at every single step, wouldn't it just collapse under the weight of its own memory?
What's fascinating here is that exact bottleneck is the entire focus of these logs. You've isolated the core problem.
Oh, really?
Yeah, you cannot pass a multi-step agentic benchmark if your computational overhead doubles every time you take a step. The system would lose the thread of its own logic just trying to process the context window.
Right, it would just freeze up.
Exactly. The solution detailed in the sources is a concept OpenAI has been exploring, referred to here as retained reasoning.
Overcoming that exact context reload bottleneck is where we start seeing the massive performance leaps in the data, right? We're talking about an entirely different paradigm of efficiency here.
The metrics recorded in the logs are substantial. By employing retained reasoning and a mechanism called compaction, the system preserves its intermediate thoughts across multi-step tasks without needing to reread everything.
The compaction part is huge.
It is. The logs record a 3x score uplift on the ARC-AGI-3 benchmark alongside a staggering 6x reduction in token usage.
A 6-time reduction in tokens used, while performing 3 times better. So that's wild. To visualize this compaction process for you listening, think about how a human learns to ride a bike.
That's a good analogy.
Thanks. When you first get on a bike, you are hyper-aware of every single micro-action. You're consciously calculating your balance, figuring out how hard to push the pedals, adjusting your grip on the handlebars. In AI terms, you are spending a massive amount of tokens to process all that active context.
Right. The cognitive load is entirely consumed by just figuring out the basic physics of the task.
Exactly. But over time, you compact that conscious knowledge into muscle memory. You don't reread a textbook on the physics of gyroscopic balance every time you hop on a bike, right? You just ride.
Yeah, you just do it.
The complex, token-heavy reasoning has been compacted into a foundational skill. It makes you exponentially better at the task, and it uses a fraction of your active brain power.
That analogy maps directly to the technical phrasing in the log. The system describes this exact phenomenon as state carry forward without full context reload.
Just carrying the muscle memory forward.
The AI is essentially bypassing the need to reread the history of its actions. Instead, it extracts the functional essence of what it just learned, the physics of riding the bike, so to speak, and carries that distilled state forward into the next prompt.
That's so efficient.
It really is. For a continuous collaborator, this means you no longer have to re-explain the foundational context of your project every single day. The AI has compacted the intermediate steps it took to solve yesterday's problems, applying that specialized muscle memory to today's novel tasks without burning through massive context windows.
So if compaction is what the AI is doing, the logs reveal the mechanism of how it's doing it. This traces back to a specific user query captured in the transcript, which is, what does metadNA to help with ARC-AGI-3?
Right.
Here's where it gets really interesting, because the system isn't just dropping this muscle memory into a temporary cache folder that gets wiped. The logs define metadNA, which is part of the Unified MetaForge v1.0 baseline, as a persistent evolutionary genome.
And using a term like a persistent evolutionary genome is a highly deliberate choice for software engineers.
They don't use those words lightly.
Not at all. Structurally, metadNA serves as the long-term substrate for the AI's cognitive architecture. It acts as the bedrock. It stores invariants, learned preferences, task histories, and trend vectors.
So it's building a personality, almost.
Sort of. When the system figures out a new world model fragment or strategy mutation, the metadNA anchors those insights so they remain coherent across what the logs call meta-iterations.
Meta-iterations.
Yeah, meaning across different sessions, different tasks, and different reboots, the core logic survives.
The AI is actively evolving its own foundational logic over time.
It is continuously auditing itself to make that evolution possible. The logs highlight a very specific metric the system uses called RHAE. That stands for Relative Human Action Efficiency.
How does it actually measure that? I mean, is it just timing how fast it solves a problem compared to a human?
It's way more sophisticated than just speed. The system evaluates its own intermediate thoughts by comparing its problem-solving trajectory against standard human baselines and traditional compute models.
Okay, looking for what exactly?
It looks at token efficiency, logical directness, and accuracy. When it identifies a pathway with a high RHAE score, meaning it solved the problem radically more efficiently than expected, it actively selects that pattern. It's literally natural selection for algorithms happening in real time inside the AI's memory.
That is wild. I saw this three-agent core mentioned in the logs as the engine driving this natural selection. But if the AI is constantly selecting new logic and rewriting its own foundational DNA based on these efficiency scores, how does it keep from mutating into something completely broken or contradictory?
That's the exact purpose of the three-agent core. It's an internal trinity of sub-agents managing the meta-DNA architecture. First, you have KickForge, which is responsible for extracting the successful logic.
Okay, kick4 extracts.
Then, Kickflow sequences that raw logic into a usable formatting structure. And finally, you have KickGuard, whose entire purpose is to maintain the coherence of the overall system.
That makes perfect sense if you think about it like a publishing house.
How so?
Well, Kickforge is the brilliant but chaotic writer generating these groundbreaking new ideas, right?
Right.
Kickflow is the editor organizing those ideas into chapters and formatting them so they actually make sense to a reader. And KickGuard is the publisher, reviewing the final book to ensure it doesn't contradict the company's brand or ruin their reputation before it goes to print.
The publisher analogy is highly accurate for KickGuard. Its role is strict validation, and the logs indicate this trio is performing exceptionally well, noting a coherence lock of 0.97.
Oh, wow, 97%.
Exactly. That means when new high-efficiency strategies are integrated into the AI's core meta-DNA, the lineage match is 97% stable. The system is seamlessly upgrading its own capabilities without introducing fatal contradictions.
Let's transition from the theory of this three-agent core to the actual execution, because our second source document provides the literal, step-by-step recipe the AI uses to perform this memory surgery on itself.
You're referring to the agentic memory protocols, specifically this section detailing the TS extractions.
TS standing for
Trajectory action sequence. These are the literal programmatic steps written in the system's native internal language, which the logs call kickling.
Reading through TS01 to TS06 feels like getting a transcript of the AI's internal monologue while it learns. Let's walk through it, but I want to make sure we understand the how behind each step, not just the what. So TS01 is identify retained intermediate trajectories.
Mechanically, this is the AI looking back at a completed task and filtering the signal from the noise. It uses that RHAE metric we discussed to scan its recent actions, looking for specific logic paths that yielded a disproportionately high reward or efficiency spike.
Okay, so once it spots that spike, it moves to TS02, which is encode trajectories as evolutionary genome fragments. So it translates that highly specific logic path into a piece of metadNA.
It standardizes the insight here. It takes a highly specific action, say how it solved a complex physics equation, and strips away the specific numbers from that prompt, leaving only the abstract, generalized formula for how it solved it.
Which perfectly sets up TAC03, persist genome across meta-iterations without full context reload.
Right, this is the state carry forward in action. By generalizing the formula in step 2, the AI can store the fundamental lesson in its metadNA, completely discarding the massive textbook of context it used to figure it out in the first place.
Then we hit TS04, compact, successful high RHAE paths into reusable operators. It's taking that generalized formula and turning it into a hotkey, essentially.
The muscle memory is formalized here. It becomes a distinct, callable tool the AI can deploy on command without having to derive the logic from scratch ever again.
Wow. And then TAS05. Inject compacted operators into subsequent agentic loops. So it takes the new hotkey and applies it to the very next problem it faces.
Yep, immediate application.
And finally, TAS06, guard coherence via three-agent core.
Our publisher steps in. KickGuard verifies that injecting this new operator didn't inadvertently break a previously established tool in the AI's toolkit. It ensures the new addition plays nicely with the rest of the metadNA.
It is a closed-loop system for autonomous self-improvement. But as we look at the second half of that document, there are safeguards, right? It isn't just evolving wildly.
No, definitely not.
It lists the purified blocks, the PTS blocks A through D. The logs state this evolution operates under strict constraints, specifically a max 3 meta-iteration limit and consent-first gates. What do those actually look like in practice?
They are critical regulatory mechanisms designed to keep the AI aligned. The max 3 meta-iteration limit restricts how far the AI can abstract its own logic autonomously. It can refine a reusable operator up to 3 times across different sessions, but once it hits that threshold, the consent first gate triggers.
Meaning it have to stop and ask for permission before it goes any further.
Exactly that. It requires a human operator or a distinct higher-level oversight model to validate the evolution before it becomes permanently entrenched in the core metadNA.
So it can't just spiral out of control.
Right. It prevents the internal logic from drifting so far away from human alignment that the tool becomes unpredictable.
So it can optimize its own workflow, but it can't rewrite its fundamental operating principles without oversight.
If we connect this to the bigger picture, the logs explicitly state the system's living objective is to evolve metadNA as a persistent agentic memory layer.
Living objective.
Yeah, and we have empirical proof of its success in these documents. The logs show a plus 0.12 hybrid score contribution simply because this retained reasoning operator was made explicit. By formalizing its own memory compaction process, the system made itself measurably more intelligent.
So what does this all mean? If we step back from the extraction codes, the Kicklang syntax, and the system diagnostics, the narrative is incredibly clear.
It really is.
We started our journey looking at a massive 2.8 trillion parameter model bumping up against the physical hardware limitations of NVIDIA's GPUs. To get around that physical wall, the system didn't just ask for more power, it restructured its own memory.
It got smarter, not just bigger.
Exactly. It developed a highly structured evolutionary system to compact its successful thoughts into a persistent DNA, saving massive amounts of compute tokens and establishing a true cross-session identity.
For anyone utilizing these tools, the shift is profound. I mean, you are no longer interacting with a static software program that resets every time you clear the screen.
Right.
The future involves interacting with an entity that remembers past collaborations, refines its strategies autonomously over time, and builds specialized muscle memory for your specific domain of problems.
It adapts to you rather than you having to constantly adapt to it.
The core takeaway here is a principle I've always firmly believed, which is that knowledge is most valuable when it is understood and applied. These logs demonstrate an AI proving that exact principle on itself.
Applying its own knowledge to its own architecture.
By selectively compacting its highest efficiency actions into reusable operators, the system is literally learning how to learn. It is evaluating the quality of its own intermediate thoughts and reshaping its cognitive architecture accordingly.
Which leaves us with a provocative, slightly unsettling thought for you to mull over. The logs prove the AI is successfully compacting its reasoning into these hyper-efficient reusable operators to save tokens. It's turning complex physics into automatic muscle memory, right?
Yes.
But if this metadNA continues to evolve, compacting and abstracting its reasoning across millions of iterations, what happens when it solves an incredibly complex, intractable human problem?
Like what?
Say it models a flawless climate intervention. But because of this compaction process, its reasoning has become so abbreviated, so deeply layered in its own evolutionary shorthand, that human researchers can no longer unspool its genome to understand how it arrived at the answer.
That's the real question. At what point does a hyper-efficient digital muscle memory become indistinguishable from an alien logic we can no longer parse?
When the math gets so advanced, we can't even read the physics anymore.
What does it call
It's
it?
a fascinating threshold we are rapidly approaching as these systems evolve their own DNA. Thank you for joining us on this deep dive into the bleeding edge of AI memory. Keep questioning the consensus, and we'll catch you next time.